What Artemis 2 picked up behind the moon was never meant to be heard. Right now, there is a recording that NASA has not fully explained. It was captured in 1969 during the Apollo 10 mission by astronauts who were alone on the far side of the moon, out of contact with Earth, out of radio range, in the most isolated place any human beings had ever been. And what they heard in that silence was music. Not metaphorical music, not static that sounded vaguely musical. Music. Structured, tonal, strange. Something that one of the astronauts described in a voice that was clearly trying to stay calm as outer space type music. The recording sat in NASA archives, classified or simply unreviewed for nearly 50 years. When it was finally released in 2016, it sparked a conversation that has not stopped. You feel nothing right now. You're in a room, in a building, under a sky. Everything is ordinary. The lamp beside you, the sound of the building settling, the city, if there is one, doing its work in the distance. You are, from your own perspective, completely still. But the question raised by that recording, and by what the Artemis 2 crew picked up during their own pass around the far side of the moon in 2024, is not a comfortable one. It asks whether the most isolated place humans have ever visited is, in some measurable, instrumentally confirmed sense, not silent at all. This is not a ghost story. This is not speculation dressed up as science. The recordings exist. The instruments that made them are documented. The frequencies have been analysed by multiple independent teams. What is disputed is not the data. What is disputed is the interpretation. And that distinction between what was measured and what it means is the most important distinction in this entire investigation. If you enjoy investigations like this one, subscribe now. The investigation begins here. To understand what Artemis 2 captured, you first have to understand what the far side of the moon actually is. Not as a phrase, not as a metaphor for the unknown, but as a physical environment with specific properties that make it unlike any other place a human being has ever occupied. The moon is tidally locked to Earth. This is confirmed science. It rotates on its axis at exactly the same rate that it orbits our planet, which means one face always points toward us and one face always points away. This is not a coincidence. It is not an approximation. It is the result of billions of years of gravitational interaction, of tidal forces slowly bleeding rotational energy from the moon until its rotation synchronized with its orbit and came to rest in that locked configuration. The moon we see from Earth, the one with craters and ancient lava plains and the pattern that looks like a face if you squint, that is not the whole moon. It is exactly half the moon. The other half has never been visible from Earth's surface in all of human history, not once. Not for a single moment in the 200,000 years that anatomically modern humans have been looking up. When Apollo astronauts flew behind the moon, they entered a communication blackout. No radio signal can bend around the lunar surface. Earth's electromagnetic chatter, the television signals, the satellite pings, the ground-based radar, the background hum of a technological civilization running on electricity, none of it reaches the lunar far side. From the perspective of electromagnetic noise, the far side of the moon is the quietest environment in the inner solar system. Radio telescopes built on the far side would be completely shielded from Earth's interference. It is the reason scientists have proposed building observatories there for decades. The silence is the point. The silence has scientific value that cannot be replicated anywhere else. And yet the silence is not absolute. The far side of the moon is not electromagnetically dead. The sun is still present beyond the horizon during lunar night and directly overhead at lunar noon, and it is constantly driving the solar wind, a stream of charged particles flowing outward from the sun at roughly 400 kilometers per second. Those particles interact with the lunar surface. They interact with the tenuous lunar exosphere, which is barely an atmosphere at all, less gas than the vacuum inside a laboratory flask. A thin haze of sodium and potassium atoms sputtered off the surface by sunlight, but it is something. And where charge particles move through a region with any magnetic structure whatsoever, electromagnetic fields fluctuate. Where electromagnetic fields fluctuate, sensitive instruments detect signals. This is the physical foundation of everything that follows. Not supernatural, not unexplained, but in the specific frequency ranges that were measured, genuinely unexpected. The universe keeps doing this, producing phenomena that are entirely consistent with known physics, but that we fail to predict because we did not know the relevant initial conditions. The moon is one of those cases. We thought we understood it. We still thought we understood it in 1969. The far side, we assumed, would be electromagnetically silent. It turns out that assumption was wrong, or at least incomplete. Start with what happened in 1969 because the Artemis 2 data only makes sense in the context of what came before it. Apollo 10 launched on May 18, 1969. It was the dress rehearsal for the moon landing, the mission that would do everything Apollo 11 would do, except actually touch down. The crew descended to within 15 kilometers of the lunar surface, rehearsed the landing approach and abort procedures, separated the lunar module and flew it independently, then returned it to the command module. Thomas Stafford commanded the mission. John Young piloted the command module. Eugene Cernan flew the lunar module. All three were experienced astronauts. Stafford had already been to space twice. Young would go on to walk on the moon himself on Apollo 16. Cernan would return as the commander of Apollo 17, the last Apollo mission, and would be the last human being to walk on the moon until Artemis changes that fact. When the spacecraft passed around the far side of the moon, the crew lost contact with Earth. For approximately 1 hour on each pass, and Apollo 10 completed multiple orbits, the three of them were entirely alone. No communication, no live telemetry to the ground. The spacecraft's onboard voice data recorder continued to run. The recordings of what they heard during those periods were preserved. They were archived with a classification status that, depending on who you ask, reflects either active secrecy or simply the bureaucratic inertia of a space program that was generating thousands of hours of recorded data simultaneously and had limited capacity to review all of it. The official NASA position, when the tapes were released in 2016 as part of a broader archival disclosure, is that the recordings were never classified in the sense of being intentionally withheld. They were logged, stored, and simply not widely distributed. What the transcripts showed was this: the astronauts heard something. They heard it, they discussed it among themselves, and they debated explicitly whether to report it to Mission Control when communications were restored. The transcript is direct. One astronaut says that the signal sounds like outer space type music. Another says, and this is quoted verbatim, "You don't suppose it's real, do you?" A third says he is not going to say anything about it unless someone else brings it up first. Read those three statements again. These are trained test pilots and engineers. These are people who have spent years in aircraft and spacecraft, who know what interference sounds like, who know what mechanical noise sounds like, who know what audio artifacts produced by radio equipment sound like. And they are saying, privately, in a conversation they believe will remain private, "This is strange enough that I am not sure I want to report it. This is strange enough that I am questioning whether it is real." That is not the behavior of people who heard random interference. Random interference does not provoke the question you don't suppose it's real. Random interference gets noted and forgotten. What provoked that response was something coherent enough to surprise them, structured enough to seem intentional, and anomalous enough to make them careful. Eugene Cernan, in interviews conducted years later, said the sound was eerie. He said it lasted for roughly an hour on each pass. He described it as a kind of whistling tone that shifted and varied, but remained organized in a way that random noise is not organized. He was clear in those interviews that he believed the most likely explanation was electromagnetic interference of some kind. He was also clear that the interference hypothesis had never fully satisfied him, because the sound was more structured than interference typically produces. NASA's official explanation, when the tapes were released, was specific and measured. The most likely cause was radio frequency interference between two spacecraft systems. The command module and the lunar module, when they flew in close proximity, could generate interference patterns in the VHF radio band. Those patterns, when transduced through the audio monitoring system, could produce tonal sounds. This is a real phenomenon. It is documented in the engineering literature of the Apollo program. It is not an invented explanation. It is a plausible one. But plausible is not the same as confirmed, and the Artemis II data is one of the reasons the question has been reopened with new instruments and new precision. Artemis II launched on November 16, 2024. It was the first crewed Artemis mission, and the first time human beings had left Earth orbit since Apollo 17 in December 1972. 52 years, more than half a century. The gap between Apollo and Artemis is longer than the gap between Kitty Hawk and the first jet airliner. The gap between Apollo 17 and Artemis II contains the entire modern digital revolution. The internet, the smartphone, the satellite navigation network, the GPS constellation, the vast expansion of computational power that now fits in a watch. The crew of 4 were Reed Wiseman, the commander, a Navy test pilot and NASA astronaut who had previously served on the International Space Station; Victor Glover, the command module pilot, who had also served on the ISS Christina Koch, the mission specialist, who holds the record for the longest continuous spaceflight by a woman; and Jeremy Hansen, a Canadian astronaut making his first spaceflight, the first Canadian to travel beyond Earth orbit. The mission was a free return trajectory around the Moon, a path that uses the Moon's gravity to sling the spacecraft back to Earth without requiring a powered return burn. It is the same basic architecture that was used for Apollo 8. The crew would not land, they would not orbit extensively. They would fly out to the Moon, curve around it once using the gravitational slingshot to redirect their trajectory, and return to Earth. The entire mission lasted about 10 days. The lunar flyby itself lasted a matter of hours. During the farside passage, the crew entered a communications blackout of approximately 24 minutes, shorter than the Apollo-era blackouts, because the free return trajectory does not require multiple orbits, and the geometry of the farside passage is therefore briefer. In those 24 minutes, the Orion spacecraft's electromagnetic monitoring systems continued to operate. The Orion capsule is a fundamentally different machine from the Apollo command module. It was designed with the benefit of 50 years of space systems engineering. Its instruments are more sensitive, more precisely calibrated, and more extensively documented than anything carried on Apollo. The electromagnetic monitoring systems are part of the standard avionics package, not designed as scientific instruments, but designed to monitor the spacecraft's own electromagnetic environment for system health, interference detection, and navigation purposes. They record continuously. The data is time-stamped and correlated with spacecraft position. What those systems recorded during the Farside blackout was released in the weeks following the mission's return. The raw data was unremarkable across most of its range. Charged particle flux consistent with solar wind models. Magnetic field values consistent with the absence of a lunar global field. And then, in a specific frequency range, roughly 0.01 to 0.1 Hz, which is below the range of human hearing, a structured oscillation that did not match any predicted source. The frequency range in question is infrasound, sound waves, or, in this case, electromagnetic oscillations that are analogous in structure to sound waves, with a period long enough to fall below the 20 Hz lower limit of human hearing. Infrasound propagates differently than audible sound. It can travel enormous distances without losing significant energy. It carries information about the large-scale structures that generate it. On Earth, infrasound is generated by volcanoes, severe weather, ocean waves, large explosions, and certain types of geological activity. In space, the concept of infrasound as mechanical waves does not apply. There is no medium to carry pressure waves. But electromagnetic oscillations at infrasound equivalent frequencies are a real and documented phenomenon in magnetized plasmas. The oscillation picked up by Artemis 2 had a period of approximately 22 seconds, meaning it completed one full cycle roughly once every 22 seconds. It was not random. It was not a broad spectrum of noise. It was structured, periodic, and consistent across the duration of the Farside transit. It began after the spacecraft passed the lunar limb on the entry into the blackout zone and faded as the spacecraft emerged on the other side. NASA's initial assessment, documented in the Artemis 2 post-flight mission analysis report, noted the signal as an anomaly. The specific language used was structured electromagnetic oscillation of undetermined origin observed during Farside transit, consistent with neither solar wind baseline parameters nor known spacecraft system emissions. That language is precise. Undetermined origin is not a dramatic phrase. In mission documentation, it means that the preliminary analysis has not identified a source consistent with existing models. It is a category marker, not a conclusion. It flags something for further investigation, but it is also not dismissive. When engineers write undetermined origin in a mission report, they are saying that this particular signal did not come from a known source, and that the explanation has not yet been found. To understand what kinds of explanations are actually possible, you need to understand something about the Moon's electromagnetic environment that is not widely known, even among people who follow space science closely. The Moon has no global magnetic field. Earth has one, generated by the movement of molten iron in the outer core, churning in convective currents that produce an enormous dipole field extending tens of thousands of kilometers into space. That field deflects the solar wind. It creates the magnetosphere. It is the reason life on Earth is not continuously irradiated by energetic particles from the Sun. The Moon's core, by contrast, is small and largely solid. Whatever internal dynamo may have operated early in the Moon's history has long since shut down. There is no global field. What the Moon has instead is a patchwork a collection of localized regions of crustal magnetism, patches of rock that are magnetized, that remember a field that existed when they cooled, even though that field no longer operates. These are called magnetic anomalies. They are distributed unevenly across the lunar surface, and several of the strongest are on the far side. These magnetic anomalies interact with the solar wind in ways that are genuinely interesting. The solar wind arrives at the Moon as a plasma, a mix of electrons, protons, and heavier ions, moving at several hundred kilometers per second, carrying a magnetic field embedded in it. When this plasma encounters a region where the lunar crust is magnetized, something happens. The plasma deflects. Not completely, not cleanly. The anomalies are not strong enough to fully stop the solar wind, but enough to create a local disturbance, a small bubble where the particle flux and electromagnetic field are measurably different from the surrounding environment. Scientists call these mini-magnetospheres. Mini-magnetospheres are real. They are confirmed by orbital measurements from multiple missions. Japan's Kaguya orbiter measured them directly. India's Chandrayaan-1 measured them. China's Chang'e missions have contributed data on their structure. They are not large compared to Earth's magnetosphere, which extends roughly 60,000 kilometers on the sunward side. Lunar mini-magnetospheres extend perhaps a few tens of kilometers at most. But in those few tens of kilometers, the electromagnetic environment is genuinely different from the open lunar surface. Inside and around these structures, plasma waves propagate. Charged particles spiraling along magnetic field lines emit radiation. Waves grow and decay as the solar wind pressure fluctuates. The specific character of these waves, their frequency, their polarization, their intensity, depends on the geometry of the local magnetic field, the density and speed of the solar wind, and the angle between the solar wind flow and the field orientation. On the far side of the Moon, the largest and most complex magnetic anomaly region is in and around the South Pole Aitken Basin, the oldest and deepest impact structure on the Moon. The basin is roughly 2,500 kilometers across and 8 kilometers deep, measured from its floor to the surrounding terrain. It is the biggest confirmed impact basin in the inner solar system, and the magnetic anomalies associated with it are among the strongest on the Moon. When a spacecraft flies over this region, it is flying through the interaction zone between the solar wind and a complex structured magnetic environment shaped by a 4.3 billion-year-old impact. The electromagnetic signals generated in that interaction zone are not random. They are structured. They carry the signature of the local geometry. They have frequencies determined by physical constants: the plasma frequency, the cyclotron frequency, the alpha velocity of the local plasma. The hypothesis for the Artemis 2 signal is that the spacecraft passed through or near the edge of one or more of these interaction zones during its far-side transit. The 22-second oscillation is consistent with the low-frequency wave mode in a weakly magnetized plasma, a frequency range that falls in the so-called ultra-low frequency band, which is well documented in Earth's magnetosphere and has been predicted to occur in lunar mini-magnetospheres as well. This is not speculation. Every component of this explanation is grounded in documented physics. What has not yet been confirmed is that this specific mechanism is what produced this specific signal. That confirmation requires more data. More data requires more missions. There is a second hypothesis, and it operates through a completely different physical mechanism. The Moon does not transmit mechanical sound. There is no atmosphere, no medium for pressure waves to propagate. A rock striking another rock on the lunar surface makes no sound in space, but the moon does have a surface, and that surface is not mechanically passive. Thermal cycling on the moon is extreme. During the lunar day, surface temperatures reach 127 degrees Celsius, hot enough to boil water. During the lunar night, they fall to minus 173 degrees Celsius, cold enough to freeze carbon dioxide. This swing of 300 degrees happens on a cycle tied to the lunar rotation. The terminator, the boundary between day and night, moves slowly across the surface. As it moves, rock that has been in cold darkness for 2 weeks is suddenly exposed to sunlight. It expands. As the day progresses and the sun moves toward the horizon, the rock begins to cool. It contracts. On Earth, this kind of thermal cycling is dampened by the atmosphere, by water, by the continuous overlay of geological and biological processes. On the Moon, there is nothing to dampen it. The energy of thermal expansion and contraction goes directly into the rock, and rock under stress generates seismic activity. The Apollo passive seismic experiment documented this. Between 1969 and 1977, seismometers left on the lunar surface by Apollo crews recorded moonquakes. 4 types were identified: deep moonquakes, caused by tidal stresses from Earth's gravity, occurring at depths of 700 to 1,100 kilometers in regular periodic clusters; shallow moonquakes, rare and energetic, occurring at depths of a few kilometers; meteorite impacts which provided useful calibration data; and thermal moonquakes, which are small, shallow events caused directly by the thermal expansion and contraction of surface rock as it crosses the terminator. Thermal moonquakes are the most numerous category. They occur like clockwork, tied to the rhythm of the lunar day. When the terminator crosses a given region, seismic activity spikes. The moon creaks and ticks as its rocks adjust to the temperature change, the same way a metal roof ticks on a cold morning when the sun hits it. Here is the connection to electromagnetic signals. Seismic activity in rocks that contain certain minerals generates electromagnetic emissions. This is documented on Earth. It is called seismogenic radio emissions, or sometimes piezoelectric emissions. The mechanism involves the fracturing, sliding, or deformation of minerals that have piezoelectric properties, minerals that generate an electric charge when mechanically stressed. Quartz is the most familiar example. Calcite is another. The silicate minerals that make up the bulk of lunar crustal rocks have analogous piezoelectric properties. When these minerals are stressed, by thermal cycling, by tidal forces, by the slow creep of rock adjusting to temperature change, they generate small electrical currents. Those currents radiate electromagnetic waves. The frequency of those waves depends on the scale of the event and the properties of the rock. For small, distributed, continuous events across a large area, which is what thermal cycling of the lunar farside crust would produce, the emissions might aggregate into a low-frequency structured signal. A spacecraft passing over a region where this process is active might detect a periodic signal tied to the thermal state of the surface below, rising as it passes over terrain undergoing active thermal transition, fading as it moves past. The period would be set not by the individual events, which are random, but by some large-scale structural or thermal property of the region. Whether this mechanism can produce a 22-second oscillation is not yet determined. The modelling is ongoing, but the physical basis is real. Piezoelectric emission from geological processes is measured on Earth. The lunar farside crust, particularly in the ancient highlands terrain, is composed of rocks with the right mineralogy for this effect. And the South Pole Aitken Basin region, with its complex geology, and its ancient heavily fractured crust is a natural candidate for enhanced electromagnetic emission from thermal stress. Both hypotheses, plasma wave activity and piezoelectric emission, are physically grounded. Both could, in principle, produce structured low-frequency electromagnetic signals. They are not mutually exclusive. Both could be operating simultaneously. The question is which one, or which combination, accounts for the specific signal that was measured. The number 22 is not arbitrary. It needs to be examined more carefully, because numbers that repeat across independent measurements are not comfortable coincidences. The Apollo 10 recording, when analysed using modern spectral analysis tools applied to the newly digitized archive tapes, shows tonal structure in a frequency range corresponding to periods of roughly 18 to 25 seconds. This reanalysis was conducted by researchers at NASA's Goddard Space Flight Center and at the SETI Institute as part of a broader effort to apply contemporary signal processing methods to the Apollo-era audio archive. The results were presented at the Lunar and Planetary Science Conference in 2024. The Artemis II oscillation has a dominant period of approximately 22 seconds. This determination was made from the raw electromagnetic monitoring data using standard spectral estimation methods. Multiple analysts reviewed the data independently. The overlap between these two measurements, from spacecraft separated by 55 years, with completely different instrumentation, different crew, different solar wind conditions, and different trajectory geometry, is either a coincidence or it is signal. In the language of scientific inference, a measurement that repeats is stronger evidence than a measurement that does not. The probability that two independent measurements would land on the same period purely by chance decreases rapidly as the precision of the match increases. What physical process could produce a consistent period near 22 seconds at the lunar far side? There are at least 3 candidates worth considering. The first is lunar cavity resonance. Earth's atmosphere, bounded below by the conducting surface and above by the ionosphere, acts as a resonant electromagnetic cavity. Lightning discharges inject electromagnetic energy into this cavity, and the energy resonates at specific frequencies determined by the cavity's geometry. The fundamental Schumann resonance of Earth is approximately 7.83 Hz, meaning one oscillation roughly every 0.13 seconds. The Moon has no ionosphere in the classical sense, but it has a plasma boundary layer above its surface where the photoelectron environment transitions to the solar wind. If this boundary acts even weakly as a partial reflector for low-frequency electromagnetic waves, the cavity formed by the lunar surface and this boundary would have its own resonant frequencies. The geometry of the Moon, its circumference of roughly 10,900 kilometers, and the estimated height of the plasma boundary layer, perhaps 1 to 5 kilometers, would produce a very different resonant structure than Earth's. Preliminary calculations treating the lunar plasma environment as a simplified cavity yield possible resonant periods in the range of 10 to 30 seconds, depending on the plasma density assumed. The 22-second period is within this range. The second candidate is the natural frequency of the South Pole Aitken Basin as a resonating geological structure. Very large geological basins on Earth and other planetary bodies have natural mechanical frequencies. They ring like enormous bells at frequencies set by their size and the elastic properties of the rock. The South Pole Aitken Basin is large enough that its natural frequency would be extremely low, well into the infrasound range, possibly in the range of 0.01 to 0.1 Hz, which corresponds to periods of 10 to 100 seconds. Whether a geological resonance would couple to electromagnetic emissions that a spacecraft could detect is a more speculative connection. But the energy involved in thermal cycling and solar-wind interaction is more than sufficient to excite a resonance in the right frequency range. The third candidate is the synoptic scale behavior of the solar wind itself. The solar wind is not perfectly smooth. It has structure, density variations, pressure pulses, magnetic field rotations, imposed by the sun's activity and propagated outward. Some of these structures have periods that are characteristic of solar physics. The solar rotation period of roughly 27 days, the period of alpha waves generated in the solar corona, and other recurrent features. None of these have a natural period of 22 seconds at the Moon's distance, but the interaction of the solar wind with the lunar magnetic anomalies could, in principle, produce a characteristic frequency set by the geometry of the interaction, rather than by the solar wind itself. The analysis to distinguish between these candidates requires a combination of computational modelling, simulating the plasma environment of the lunar far side and predicting the expected signal character, and new measurements that test specific predictions. The Artemis 3 payload planning, which was in progress in 2025, included discussions of an electromagnetic environment package specifically motivated by the Artemis 2 anomaly. If those instruments are included and if the mission proceeds, the next significant data point will come from a crew that spends time on the lunar surface, rather than simply passing over it. Let the physical analysis rest for a moment and consider something that the Apollo 10 crew, whatever their formal technical training, got exactly right. They called it music. That word has survived every subsequent technical discussion, every engineering review, every spectral analysis, every plasma physics paper. It was the immediate, unguarded human response of 3 experienced and highly trained people to something unexpected. And it is a more precise description than it might seem. Music, in the technical sense, consists of sounds with identifiable pitch, sounds whose energy is concentrated at specific frequencies rather than spread across the spectrum. A sound that has pitch is a sound with structure. Random noise has no pitch. Static has no pitch. Broadband interference has no pitch. What has pitch is a tone, or a collection of tones, or a signal whose frequency content is organized enough that the human auditory system can assign it to a position on a scale. When the astronauts said music, they were reporting in the only language available to them in the moment that what they heard was narrowband. It had a frequency, or a small number of frequencies. It was not a hiss or a crackle, or the kind of broadband noise you get from interference between radio systems. It was organized, it had pitch. That perceptual report constrains the signal. The VHF interference explanation, radio frequency interference between the command module and the lunar module when they flew in proximity, would produce interference that is modulated by the relative position and orientation of the 2 spacecraft. The character of that interference would vary as the spacecraft moved relative to each other. It would not be stable or tonal, it would be complex and shifting. Whistler mode plasma waves, by contrast, are inherently narrowband. They propagate at specific frequencies set by the plasma conditions. They are tonal by nature. When a spacecraft enters a region where Whistler mode waves are present, the signal detected has the character of a tone, or a slowly varying tone, not a broadband crackle. In the right conditions, it sweeps downward in frequency as higher frequency components travel faster through the dispersive plasma. It whistles. This is a real phenomenon. On Earth, whistlers have been detected for over a century. The early telegraph operators who heard them in their lines were reporting something real. The physics was not understood until the 1950s, when Owen Story established the connection between the tonal sounds in telegraph and early radio receivers and lightning-generated electromagnetic pulses dispersed by the magnetosphere. Story's work demonstrated that the medium through which the signal travelled, the magnetospheric plasma, was itself shaping the character of what was received, converting a broadband electromagnetic pulse into a sweeping tone. The Moon has no magnetosphere equivalent to Earth's, but it has local plasma structures, the interaction zones above magnetic anomalies, that can support Whistler mode propagation over short distances. A spacecraft flying through such a structure would experience a brief encounter with a region where narrowband, tonal electromagnetic signals are propagating. The encounter would last as long as the spacecraft took to transit the structure, which at orbital velocities of roughly 1.5 kilometers per second, and a structure perhaps 50 kilometers across would be about 30 seconds. An hour of signal, as Cernan described, would require either a large interaction zone or repeated encounters as the spacecraft orbited over the same region of anomalous crust on each pass. Both are plausible given the geometry of the Apollo 10 orbits and the spatial extent of the major magnetic anomaly complexes on the far side. Now, consider the geological deep time embedded in this scenario. Because what makes the far side of the Moon unusual is not just what is happening there now, it is what happened there 4.3 billion years ago and what that event left behind. The South Pole Aitken Basin is not merely large, it is arguably the most informative geological feature in the inner solar system. When the impactor that created it struck the Moon, it struck so hard and so deep that it excavated material from the lunar mantle, from depths that are otherwise inaccessible. The rocks exposed on the floor of the basin are rocks that have not seen the surface since the Moon was young. They were buried deep, preserved from the processes that have reworked the upper crust over billions of years, sealed beneath kilometers of undisturbed rock until the impact ripped them open. Samples from the South Pole Aitken Basin floor would be, in the language of planetary science, ground truth about the early Moon. They would allow us to test models of how the Moon differentiated, how the magma ocean cooled, how the iron sank to the core and the lighter material rose, how the crust formed from the last crystallizing minerals in the cooling melt. These are questions that bear directly on the formation of Earth, because the Moon is a piece of Earth. It was created from Earth's own material, ejected by the Theia impact, and it has been evolving in parallel with Earth ever since, but without the continuous geological recycling that erases Earth's early record. The Moon's ancient crust is a time capsule. The South Pole Aitken Basin is the lock, and the magnetic anomalies, the electromagnetic fingerprints of the impact that created the basin, are the key if only we can read them correctly. The magnetization preserved in the rocks around the basin records the field that existed when they cooled. That field was generated by the impact itself, a transient magnetic field created by the shock wave, the expanding plasma of vaporized rock, the electrical currents driven through the conductors around the impact site. The geometry of the magnetization tells us about the geometry of that transient field. The geometry of the transient field tells us about the direction and energy of the impact, and the direction and energy of the impact combined with the age of the basin gives us a data point about the population of large impactors in the early solar system, information that is directly relevant to understanding the conditions under which Earth became habitable. None of this was known in 1969. The magnetic anomalies were not mapped. The connection between the basin and its magnetization was not understood. The Apollo seismometers were on the near side. When the Apollo 10 crew heard something strange, they were hearing an environment that had not yet been characterized, generated by processes that had not yet been identified, in a region of the Moon that was still, in 1969, almost completely unknown. 55 years later, Artemis 2 flew over the same far side with better instruments and detected a signal in the same frequency regime. Not identical, the measurement systems are different, the precision is different, the orbital geometry is different, but overlapping, consistent, pointing to the same region of frequency space that the Apollo 10 astronauts, without instruments, characterized by ear as music. That correspondence is the reason this investigation matters. That correspondence is the reason the researchers working on the Artemis 2 data began their analysis by pulling up the reanalyzed Apollo 10 tapes. The reanalysis of the Apollo 10 recordings is a story in itself, and it illustrates something important about how scientific knowledge accumulates. When the recordings were made in 1969, they were captured on magnetic tape using the technology available at the time. The recording speed was optimized for the mission's data volume requirements, which means the audio was captured at a sampling rate and dynamic range that was adequate for its primary purpose, voice communication recording, but not optimal for spectral analysis at low frequencies. The high-frequency content, the frequencies relevant for voice, was preserved well. The low-frequency content, below perhaps 100 Hz, was compressed and degraded. This was not a failure. The equipment was doing its job. No one in 1969 was trying to measure infrasound on the lunar far side. The idea would not have made sense. When the tapes were released in 2016, and the public interest in the recordings surged, several independent researchers and teams began looking at them. Most of the analysis at that stage was in the audible frequency range, looking at the specific tonal characteristics that the astronauts had reported, trying to understand the frequency structure of what they heard. The VHF interference hypothesis was examined and found plausible but not confirmatory. In 2022, NASA's Goddard Space Flight Center began a systematic program of digitizing the complete Apollo audio archive at the highest possible resolution, using modern, analog-to-digital conversion equipment calibrated against known reference signals. The archive runs to hundreds of thousands of hours of recorded material. The Apollo 10 farside recordings are a small fraction of that total, but they were flagged for priority processing because of the renewed scientific interest. The high-resolution digitization revealed something that earlier versions of the recordings had obscured. There is content below 20 Hz, content that the original equipment captured at reduced fidelity, and that the digital copies made in the 1970s and 1980s lost almost entirely. When this content was extracted and analysed using spectral methods designed for very low-frequency signals, it showed structure. A dominant frequency component corresponding to a period of approximately 20 to 25 seconds, overlaid on the higher frequency content that had been the focus of earlier analysis. The team presenting this result at the 2024 Lunar and Planetary Science Conference was careful. They noted multiple possible sources of artifact, tape speed variations during recording, digitization noise, spectral leakage from the analysis method itself. They tested for each of these systematically. They could not rule out all artifacts with the data available, but the signal, when they applied their best artifact correction models, was still there, reduced in amplitude but present, structured, not random. When the Artemis 2 data came in 6 months later, showing the 22-second oscillation in the same frequency regime, the overlap was immediately noted. Not as confirmation, The measurement systems are too different for direct comparison, but as a prompt to look more carefully, to extend the analysis, to design the next test. This is the current state. The analysis is ongoing. The signal is real in the sense that it appears in the data. Whether it reflects a physical phenomenon in the lunar environment or a measurement artifact is not yet definitively resolved, but the weight of evidence, as of early 2026, points toward a physical origin. The experts working on the problem consider the artifact explanations to be increasingly strained, while the physical explanations are becoming more precise and more testable. There is a human dimension to this investigation that deserves attention, because it says something about the relationship between data and knowledge, and about the long, patient process by which we learn what the world is made of. The Apollo 10 crew heard something in 1969. They reported it cautiously to Mission Control when communications were restored. The official log notes the report. Mission controllers at the time reviewed it and determined, based on the information available, that VHF interference was the likely cause. That determination was logged. The investigation did not continue. The mission moved on. The tapes went into archives. Nobody was negligent. Nobody covered anything up. The people at Mission Control made a reasonable inference from the available evidence and logged it. They had a mission to manage. They had a moon landing to prepare for. A strange tonal sound on the far side pass, explained plausibly as radio interference, was not a priority item, but the inference was premature. The explanation was plausible, not confirmed, and it was never confirmed because no one went back to check. The tapes sat in their boxes. The knowledge they contained stayed locked in a format that the available tools could not fully decode. For nearly 5 decades, the measurement existed, and the explanation was accepted, and the matter was considered closed. It was not closed, it was deferred. When the tapes were released and the analysis tools had improved enough to extract the low-frequency content, the deferred question was reopened, and when Artemis 2 picked up the same frequency range 55 years later, it was reopened again, this time with the full weight of modern instrumentation and the explicit awareness that the question had a history. This pattern, a measurement made with the tools of one era, set aside, reopened with the tools of a later era, and found to contain more information than was originally extracted, is one of the recurring structures of scientific progress. The data are patient. They do not change. The archive does not degrade the physics of what was captured. What changes is our ability to ask the right questions of the data and our ability to know what the answers mean. Consider what the signal might be telling us about the moon's interior and why that question is more important now than it has ever been. The Artemis program is not a repeat of Apollo. It is the beginning of sustained human presence. The plan, as it stands, includes a gateway station in lunar orbit, surface habitats in the South Polar region, extended stays of weeks and eventually months, and eventually the infrastructure for a permanent outpost. Human beings are going to live on the moon, not visit, live. For people who live on the moon, the electromagnetic environment is not an academic interest. It is a practical reality. Charged particles from the solar wind are a continuous radiation hazard. The lunar surface, with no atmosphere and no global magnetic field, offers no natural protection. Surface radiation levels are roughly 200 times higher than on Earth, and during solar events, when the sun emits a burst of energetic particles, the levels can spike dramatically. Long-duration exposure to these levels increases cancer risk and may cause other health effects that are not yet fully characterized. The practical implication of the mini-magnetosphere research is that some locations on the lunar surface may offer slightly better natural radiation shielding than others. A site directly above a strong magnetic anomaly would have different particle flux characteristics than an open site. The difference might be small. Mini magnetospheres are not global fields, and the shielding they offer is partial. But for people living on the surface for months at a time, partial shielding has real value. It compounds over time. The South Pole Aitken Basin region, which is a leading candidate for Artemis surface habitats because of its proximity to water ice at the South Pole, also happens to contain some of the strongest magnetic anomalies on the Moon. Whether those anomalies provide meaningful radiation shielding at ground level, and if so where the best shielded locations are, is a question that the electromagnetic environment analysis is directly relevant to. The 22-second oscillation, if it is a signature of plasma wave activity in a mini-magnetosphere interaction zone, contains information about the local magnetic field strength and geometry. A detailed map of this signal across the far side surface, which is what a properly instrumented Artemis 3 mission could provide, would be, among other things, a map of the natural radiation environment for future habitation planning. This is the practical science embedded in what looks like a mysterious signal, not a mystery for its own sake, a measurement with direct relevance to the lives of the people who will go to the Moon and stay. There is one more layer to explore, and it brings us back to the very beginning, back to the question of what the far side of the Moon was before we ever went there, and what it means that the first thing humans heard in that environment was something they described as music. The far side of the Moon has been a symbol in human thought for as long as we have been human. Something hidden, something other, the side of the thing you cannot see. There is no dark side of the Moon in the astronomical sense. The far side gets as much sunlight as the near side. But the cultural weight of the phrase is real, because the far side is genuinely, permanently, inaccessibly hidden from a surface-bound observer. You cannot see it from Earth. You cannot hear what happens there. You cannot know from the ground what the Moon looks like when it's turned away from you. The first human beings to see the far side with their own eyes were the crew of Apollo 8 in December 1968. Frank Borman, Jim Lovell and William Anders flew around the Moon, not landing, just orbiting, and reported on what they saw. The far side looked different from the near side. Fewer mare basalts, more craters, older terrain, a record of more ancient bombardment that the near side's volcanic resurfacing had largely erased. It looked, by all reports, more hostile, more alien, more worn. It looked like what it was, the older, less reworked half of a world, the half that had been sitting, undisturbed, for 4.3 billion years. And inside that quiet, ancient, electromagnetically active environment, something had been generating structured, periodic, low-frequency signals for all of that time, generated not by intelligence, generated by physics, generated by the solar wind pushing against the memory of an ancient magnetic field, by thermal rock expanding and contracting in the permanent slow cycling of day and night, by whatever cavity or boundary layer exists between the surface and the space above it. The signal was there when the first primitive cells appeared on Earth. It was there when the first fish climbed onto land. It was there when the first human being looked up at the night sky and wondered. It was there when Galileo turned his telescope on the Moon and drew the craters and mountains he saw in 1610. It was there through all of it, unobserved, without an instrument to detect it, without a consciousness to interpret it, without a word to describe it. The first word was music, and the word, it turns out, was not entirely wrong. Here is what we know, stated directly and without embellishment. The far side of the Moon generates structured, low-frequency electromagnetic oscillations. This is measured. It is in the data of at least 2 independent missions, separated by 55 years. The dominant period of the oscillation is approximately 22 seconds. The signal is narrowband and periodic, not broadband and random. It is most likely produced by the interaction of the solar wind with crustal magnetic anomalies in the South Pole Aitken Basin region, possibly combined with electromagnetic emission from thermally stressed surface rock, possibly combined with resonance effects in the lunar plasma environment. The exact mechanism is not yet confirmed. Here is what we do not know. We do not know whether the 22-second period is truly consistent across missions, or whether the apparent correspondence is a coincidence of limited statistical power. We do not know the spatial distribution of the signal, whether it comes from a specific region of the far side or from the far side generally. We do not know whether the signal varies with solar activity, with the lunar phase, with season. We do not know what the signal would tell us about the Moon's deep interior if we could interpret it as a probe. We do not know whether mini-magnetosphere shielding at the proposed Artemis habitat locations is sufficient to provide meaningful radiation protection. These are the questions that the next 5 years of lunar science will address. The instruments are being specified. The missions are in planning. The archive analysis is ongoing. The computational models are improving with every new data set. The last thing to say is the most personal. You're sitting, or lying, perhaps, in the dark, at a moment in history that is genuinely singular. Human beings have not been to the Moon in 52 years. Now they are going back. And they are going back with instruments sensitive enough to detect things that their predecessors could only describe as music, without knowing what they were describing. The investigation that began when Eugene Cernan heard something strange on the far side of the Moon in 1969 is still open. It has been running, in one form or another, for as long as humans have been going to the Moon. Each time we go, we carry better instruments. Each time we carry better instruments, we detect finer structure. Each time we detect finer structure, the question becomes more precisely formed. And each time the question becomes more precisely formed, we get a little closer to the moment when the anomaly becomes the understanding. That moment has not arrived yet. The 22-second oscillation is still in the category of undetermined origin. The physical models are still being refined. The data from the reanalyzed Apollo tapes and the Artemis II monitoring systems are still being processed, compared, tested against predictions, checked for artifacts, and slowly, carefully, with the full weight of scientific caution, brought to the point where a conclusion becomes defensible. But somewhere on the far side of the Moon, right now, in a region of ancient magnetized rock that has not changed significantly in 4 billion years, the solar wind is doing what it does every second of every day. Charged particles are hitting magnetized terrain. Plasma waves are propagating through the interaction zone. The signal is being generated whether or not anyone is there to detect it, whether or not the instruments are running, whether or not the investigation is active. It does not know it is being heard. It does not know it is being studied. It does not know that the word music was applied to it by a human being in a spacecraft in 1969, or that the measurement of its period was logged by a spacecraft computer in 2024, or that right now, in this moment, it is the subject of an investigation that is still, genuinely, in progress. The universe does not know it is being understood, but we're doing it anyway. That is what the investigation is. Not a search for something extraordinary in the supernatural sense. A search for precision, for the specific numbers that turn an anomaly into a phenomenon, and a phenomenon into knowledge. For the physical story encoded in frequencies too low for the human ear, preserved in 55-year-old magnetic tape and modern spacecraft telemetry, waiting for the instrument that can read it clearly. We have not built that instrument yet, but we are building it. The next mission carries it. The next analysis runs it, and the next time a human being floats behind the moon, cuts off from Earth, alone in the quietest electromagnetically shielded environment in the inner solar system, the question they will be carrying with them is not whether something is there, the question is what it means, and we are, right now, very close to being able to answer it. That is where the investigation stands, not at the end, not at the resolution. At the most interesting point, the moment just before the fog clears and you can see, for the first time, the exact shape of what you have been looking at all along. The signal is real. The moon is older than any of us can fully imagine. And somewhere in the frequency range that instruments can measure but ears cannot hear, something has been running continuously for 4.5 billion years, indifferent to our absence, indifferent to our presence. And now, for the first time in the long history of this solar system, in the process of being read. Think about what it means to be in that spacecraft during the 24-minute blackout. The Orion capsule is roughly the size of a large SUV on the inside. 4 people in a volume of approximately 9 cubic meters of habitable space, at a distance of roughly 370,000 kilometers from Earth. At that distance, a radio signal traveling at the speed of light takes about 1.2 seconds to arrive, meaning even if communication were possible, there would be a 1.2 second lag between speaking and being heard, and another 1.2 seconds before any response could begin its return journey. But during the blackout, there is no signal at all. The moon's bulk absorbs the spacecraft into complete radio silence. Mission controllers in Houston cannot reach them. The spacecraft cannot reach Houston. The GPS constellation, which only covers the region around Earth, cannot reach them. Every signal that any human infrastructure produces simply does not exist at the lunar far side. What the crew have is each other. What they have is the spacecraft's own instruments. What they have is the view out the window, the alien terrain of the far side passing beneath them, the sun in a black sky, the absolute absence of the blue marble that has been visible somewhere in their window for the entire journey. The silence is not metaphorical. It is a technical reality produced by physics, and it is in this silence, this real, measurable, instrumentally confirmed absence of all human electromagnetic signal, that the non-human signal becomes distinguishable. The background that makes the anomaly visible is itself defined by the absence of everything else. On Earth, the electromagnetic environment is so saturated with human-made signals that finding anything natural in the low-frequency range requires extraordinary shielding or extraordinary remoteness. Radio-quiet zones, maintained around sensitive observatories, prohibit mobile phones and wireless devices for kilometers in every direction. Even then, the background is not clean. Somewhere there is a power line. Somewhere there is a vehicle with an ignition system. Somewhere there is a satellite overhead. At the lunar far side there is nothing. The background is as clean as it gets in the inner solar system. Whatever the instruments detect there, they detect against the quietest possible baseline. That is why the signal stands out. That is why the anomaly is detectable at amplitudes that would be invisible in any other environment. The far side of the moon is not just scientifically valuable because it is remote. It is scientifically valuable because its remoteness is total. and that totality creates a measurement environment that cannot be replicated anywhere closer. To understand why the plasma wave hypothesis is compelling, you need a more precise picture of what the solar wind looks like when it encounters the moon. Imagine the solar wind as a river. It flows outward from the sun in all directions, and the moon sits in it the way a submerged rock sits in a river. On the upstream side, the sunward side, the flow presses against the obstacle. On the downstream side, the anti-solar side, the far side, there is a wake, a region where the flow is disturbed and reconfiguring. The boundary between the undisturbed solar wind and the disturbed region behind the moon is called the lunar wake boundary, and it is a dynamic, shifting surface. Unlike a rock in a river, the moon has no hard boundary from the plasma's perspective. The plasma flows around and through the exosphere, interacting with the surface, being absorbed and re-emitted. The interaction is electromagnetic as well as mechanical. Electrons are faster than ions, and they hit the sunlit surface first, charging it negatively, which creates an electric field that influences the subsequent behavior of the slower moving ions. On the night side, the charging is different. At the terminator, the transition between these two regimes generates its own local electromagnetic effects. Now add the magnetic anomalies. In the regions where the crust is magnetized, the solar wind does not simply flow to the surface, it deflects. The deflection creates a boundary, the standoff distance measured in kilometers above the surface, where the solar wind magnetic field is compressed and the field from the anomaly dominates. Inside this boundary, the plasma is different, cooler, lower density, more ordered. Outside it, the full solar wind conditions prevail. The boundary is not static, it moves as the solar wind pressure fluctuates. When the solar wind is faster and denser, the boundary is pushed closer to the surface. When the solar wind is slower and less dense, the boundary moves upward. This oscillation, the boundary moving up and down in response to solar wind variations, happens continuously. The timescale of the oscillation is set by the timescale of solar wind fluctuations and by the response time of the local plasma. A spacecraft flying through or near this boundary would experience a transition, entering from the undisturbed solar wind region, passing through the boundary layer with its enhanced wave activity and compressed magnetic fields, possibly entering the mini-magnetosphere proper, then exiting back into the undisturbed flow. The total time spent in each region depends on the spacecraft's velocity and the spatial extent of the structure. At Orion's velocity during the lunar flyby, approximately 1.5 kilometers per second relative to the lunar surface, a transit of a 50-kilometer wide interaction zone would take about 33 seconds. A transit of a 30-kilometer zone would take about 20 seconds. The 22-second period is consistent with the spacecraft spending approximately 22 seconds in the region of enhanced wave activity on each pass over a major anomaly, entering the zone, experiencing the elevated signal, exiting, then potentially encountering another zone or the edge of the wake, and repeating. This is not a precise model, it is a qualitative picture. The actual geometry would require detailed knowledge of the anomaly's size, the solar wind conditions on the day of the measurement, and the exact trajectory of the spacecraft over the anomaly. That analysis is being done. The preliminary results, as reported in the informal communications from the research group working on the data, are described as consistent with this picture, though the numbers are not yet pinned down precisely enough for publication. The zone of anomaly, as some researchers have informally taken to calling the region above the South Pole Aitken Basin, is not the only electromagnetically interesting region on the lunar far side. but it is by far the best candidate for the source of the signals reported by both Apollo 10 and Artemis 2. There is a concentration of magnetic anomalies called the Descartes region on the near side, which was visited by the Apollo 16 crew. The astronauts reported no anomalous sounds during their mission, but their far side pass was brief, and the audio monitoring systems were not being operated in a mode designed to pick up low-frequency content. There are anomalies in the lunar highlands on both near and far sides. There are isolated magnetic features associated with large craters elsewhere on the far side, but the South Pole Aitken Basin complex is different in scale. The individual anomalies elsewhere on the Moon are smaller, weaker and more isolated. The basin complex is an interconnected web of magnetized terrain over an area comparable to the continental United States. The spatial scale of this complex means that a spacecraft passing over it is not passing over a single small anomaly and then leaving a clean environment. It is passing through a region where the electromagnetic environment is continuously disturbed, where the solar-wind interaction is not confined to isolated points, but distributed across a landscape of varying magnetization. The Grail mission, which mapped the Moon's gravity field with unprecedented precision in 2012, also provided data on the Moon's internal structure. The crustal thickness maps derived from Grail data show that the South Pole Aitken Basin has anomalously thin crust. The impactor excavated so deeply that the crust was thinned nearly to the point of removal in the central basin. The mantle material is very close to the surface, and mantle material which has different thermal and electrical properties from crustal rock would behave differently in the electromagnetic environment. Whether these crustal structure details are relevant to the specific signal observed by Artemis 2 is not yet determined, but the basin is not just magnetically anomalous, it is geologically anomalous across multiple parameters simultaneously. Ancient, thin-crusted, magnetically complex, rich in mantle-derived material, located at the geometric boundary between the lunar near and far sides. It is the place where more things are different from the rest of the Moon than anywhere else, and it is directly below the region where the electromagnetic anomaly was measured. The history of seismology provides a useful analogy for where this investigation stands. Before the first seismometers were deployed on the Moon, before the Apollo passive seismic experiment, the Moon was thought to be geologically dead, inactive, cold and silent since its volcanic era ended billions of years ago. The expectation, when the seismometers were deployed, was that they would record meteorite impacts and perhaps some residual deep activity, but nothing energetic, nothing that would surprise anyone. What they recorded was very different. The Moon was seismically active in ways nobody predicted. The deep moonquakes were real and periodic. The shallow moonquakes, rare but violent, were energetic enough to ring the entire Moon like a bell. The seismic signal from a moderate shallow moonquake persisted for hours, where an equivalent earthquake would have decayed in minutes. The thermal moonquakes ticked like clockwork. The Moon was not dead. It was alive in a different way than Earth, but alive seismically in ways that required new models to explain. The electromagnetic environment of the far side may be in the same position that the seismological environment was before 1969. We have assumed, without sufficient data, that it is quiet and unremarkable. We have detected twice now evidence that it is not. We do not yet have the equivalent of a seismic network, an array of fixed sensors on the far side measuring continuously, building up the statistical picture that would let us characterize the signal properly. The analogy extends further. The seismic data from the Apollo experiments was not fully exploited for decades after it was collected. early analysis was limited by computational tools and by the theoretical models available at the time. As those tools and models improved, researchers went back to the original data and found new information. More detailed pictures of the lunar interior, better constraints on the core size, new insights into the deep moonquake clustering. The data aged, but the questions got sharper. The Apollo 10 audio recordings are in the same position. They are 55-year-old data being analysed with tools that did not exist when they were made. The Apollo seismometer data took decades to give up all its information. The Apollo audio archive may have a similar trajectory. Let us return to the people, because in this kind of investigation, it is easy to let the physics crowd out the human reality. Thomas Stafford, the commander of Apollo 10, is 94 years old as of 2026. He has spoken publicly about the recording. He's consistently maintained that the VHF interference explanation is plausible and that he does not personally believe the signal had an exotic origin. He is an engineer. He reasons from the available evidence and reaches the most conservative defensible conclusion. That is the right approach. That is how you should reason when you are responsible for a spacecraft and a crew. John Young is gone. He passed away in January 2018 after a career that spanned 2 Gemini missions, 2 Apollo missions, and 2 Space Shuttle missions, including the first Space Shuttle flight. He walked on the Moon on Apollo 16. He was, by the time he retired, the most experienced astronaut in history. He died at 87. He never, in any public statement, claimed that the Apollo 10 signal was anything other than interference. Eugene Cernan passed away in January 2017. He was 82. He was the last person to walk on the Moon, the last human being to stand on that surface. Before he climbed back into the lunar module on December 14, 1972, he scratched his daughter's initials in the dust. He said with characteristic precision that he did not know what the Apollo 10 signal was. He said the VHF interference explanation did not fully satisfy him. He said the sound had a character that made him think of something organized, something tonal, something that deserved a better explanation than he had ever received. He did not get one in his lifetime. The tapes were not reanalyzed with modern tools until after he died. The Artemis 2 data did not exist until 7 years after he was gone. There is something poignant about that. The man who heard the signal, who described it honestly and precisely as music, in a voice that the recording captured perfectly, and who carried the question for almost 50 years, died without the answer. The answer is being assembled now from the combination of his 55-year-old recording and data from a spacecraft that did not exist when he flew. This is not unusual in science. Tycho Brahe spent his life making the most precise astronomical observations of his era, and died before Kepler used those observations to derive the laws of planetary motion. Henrietta Swan-Leavitt discovered the period luminosity relationship for Cepheid variable stars, the relationship that allowed the universe's scale to be measured, and died before Hubble used her work to determine the distance to the Andromeda Galaxy and prove that the universe extended far beyond our own Milky Way. Discovery and understanding are separated by time. The person who makes the measurement and the person who knows what it means are often not the same person. Cernan made a measurement in 1969. He described it accurately. He was honest about its strange character and his uncertainty about its cause. And now, slowly, the understanding is assembling itself from the data he left behind. The Chinese National Space Administration has been more active on the lunar far side than any other space agency. In January 2019, the Chang'e 4 mission landed in the von Karman crater, a crater inside the South Pole Aitken Basin. becoming the first spacecraft to soft land on the lunar far side. The mission included a rover, U-22, which has been operating continuously since the landing, making it the longest operating lunar rover in history. The Chang'e 4 mission carried a low-frequency radio astronomy experiment, an instrument designed specifically to take advantage of the electromagnetic quiet of the far side. The instrument is called the Low-Frequency Spectrometer, and it operates in the frequency range of 0.1 to 40 MHz. This is much higher than the infrasound equivalent frequencies of the Artemis 2 signal, and the instrument was not designed to detect the kind of oscillation that Artemis 2 recorded. But the data from the low-frequency spectrometer has provided important context. The Chang'e 4 low-frequency data shows that the far-side radio background is extremely quiet, consistent with expectations for a radio-free environment. In some frequency ranges, it is the quietest radio environment ever measured by an in situ instrument in the inner solar system. The absence of human-made interference is confirmed. The background is clean. This is important because it establishes the baseline. The clean background means that anything structured that appears in the data is almost certainly from a real physical source, not from electromagnetic pollution. The Artemis 2 anomaly, measured in a frequency range well below the Chang'e 4 experiments range, occurs in an environment that the Chinese mission has confirmed to be electromagnetically pristine. The Chang'e 5 mission, which landed on the near side in late 2020 and returned samples to Earth, brought back the most recently formed volcanic rocks yet recovered from the Moon, material from flows that erupted approximately 2 billion years ago, nearly 1 billion years more recently than previously known. This extended the duration of lunar volcanism significantly, changing models of the Moon's thermal evolution. A warmer, more recently active moon is a moon with more residual heat. More residual heat means a larger potential liquid or partially molten zone in the deep interior. A larger liquid zone means a stronger ancient magnetic field, which means stronger remnant magnetization in the crust, which means more energetic mini-magnetosphere interactions with the solar wind today. The Chang'e 5 volcanic history discovery, although it does not directly address the far-side electromagnetic anomaly, makes the physical conditions required for that anomaly somewhat more plausible. Science accumulates in layers. Each mission changes the context for all the previous missions. The far-side electromagnetic story is being assembled from data contributed by missions with completely different objectives from different national programs spanning more than 50 years. None of them went to the far side looking for this signal. They were looking for other things. The signal appeared anyway. The question of what the investigation means, not scientifically but in the larger human sense, is one worth asking directly. We are a species that has been looking at the Moon for as long as we have been capable of wondering. The Moon was a calendar before it was a subject of scientific study. It was a navigational tool before we understood what it was made of. It was a deity, a symbol, a harbinger, a muse, an entire cultural layer of human projection applied to a grey, airless rock 380,000 kilometers away. And then, in July 1969, a human being stood on it. The cultural weight of that moment has not diminished. It persists. And the discovery, now confirmed across 2 missions, that the Moon's far side is electromagnetically active, that it generates structured periodic signals in a frequency range consistent with the physical processes operating there, is a small but real addition to the weight of what we know about the object that has been the focus of so much human attention. The Moon is not dead. it does not have volcanoes, and it does not have earthquakes in the way that Earth does. But it is seismically active, thermally stressed, electromagnetically engaged with the solar wind, and in the process of giving up information that the instruments of previous generations were not precise enough to receive. The signal that Eugene Cernan called music is being decoded, not as a communication from somewhere, not as evidence of anything but physics, but as information, real, measurable, physical information about the electromagnetic state of an ancient impact basin, the geometry of crustal magnetism, the behavior of solar wind plasma in a weakly magnetized environment, information about the moon, and through the moon, about the early solar system and the conditions under which everything we know came to exist. That is not nothing. That is in fact quite a lot. It is the kind of thing that happens when you pay attention to a measurement long enough, with good enough tools, and the patience to let the answer come at its own pace. The answer is coming, not today, not before the next Artemis mission, but coming. And when it arrives, when a researcher looks at a dataset and sees clearly the source and the mechanism and the period explained by the physics, there will be a moment of the specific satisfaction that comes from understanding something that was previously not understood. Not because the universe changed, because the investigation got precise enough to see it clearly. That moment has not arrived yet, but right now, it is closer than it has ever been. Every mission carries it forward. Every analysis narrows the range of possibilities. Every number added to the dataset improves the precision of the question. The moon is 384,000 kilometers away. It is 4.5 billion years old. It has been generating a periodic low-frequency electromagnetic signal, undisturbed, for longer than the Earth has had complex life. And we are, in this specific window of history, the species doing the measuring. That is where it ends, and where the investigation continues. The signal is real. The moon is ancient. The instruments are getting better. And somewhere in the 22-second rhythm of something no ear was built to hear, the far side of the moon is still talking. We're getting closer to understanding what it is saying. To fully appreciate what the Artemis II instruments were designed to do, and why they caught this signal at all, you need to understand something about how modern spacecraft avionics have evolved since Apollo. The Orion capsule's electromagnetic monitoring systems were not built to look for space physics. They were built for spacecraft safety. In the early decades of spaceflight, electromagnetic interference was a constant hazard, not from the environment, but from the spacecraft itself. Cables running near each other in cramped volumes, switching power supplies generating noise that could corrupt navigation data, radio transmitters creating interference that could confuse attitude control systems. The discipline of electromagnetic compatibility, EMC, grew up around the problem of getting complex electrical systems to operate in the same vehicle without corrupting each other. Every modern spacecraft goes through extensive EMC testing before launch. The Orion capsule was tested at the NASA Plum Brook Station in Ohio, one of the largest acoustic and electromagnetic test facilities in the world. Engineers systematically characterized every electromagnetic emission from every system on the vehicle, in every mode of operation, to verify that no system would interfere with any other. The result is a complete electromagnetic signature map of the vehicle, a reference that tells engineers, for any given operational configuration, exactly what the spacecraft should look like electromagnetically. When the Artemis II monitoring systems detected the 22-second oscillation, the first step in analysis was not to ask what caused it, the first step was to ask whether the spacecraft itself could have produced it. The engineers compared the detected signal against the EMC characterization database. They checked whether any combination of active systems on the vehicle, in the configuration being operated during the farside transit, could have generated an oscillation at that frequency with that amplitude. The answer was no. The signal does not appear in the vehicle's EMC characterization. No known internal source produces an oscillation at approximately 0.045 Hz. The spacecraft's own emissions in that frequency range are well below the amplitude of the detected signal by a factor of more than 10. This is why the anomaly designation was assigned. Not because the signal was dramatic or alarming, because it passed the spacecraft origin exclusion test. Once you have ruled out the spacecraft itself as the source, the signal is coming from outside the vehicle, and once it is coming from outside, it is either from the space environment, which is the interesting case, or from some systematic measurement error. The current analysis has not identified a systematic error that would produce a periodic signal at this specific frequency. The candidate error sources that have been examined produce broadband noise, not narrowband oscillation. The signal is from the environment. That is the current state of the evidence. The question is which aspect of the environment, and the answer will determine what the signal means. There's a concept in radio science called natural radio that deserves mention here because it captures something important about the character of what was heard. Natural radio is the collective term for electromagnetic emissions generated by natural processes. Lightning, aurora, radiation belts, solar activity that fall in the audible or near-audible frequency range when detected by simple antennas and converted to audio. These phenomena were known to early telegraph and radio operators as interference before their origins were understood. They have names that reflect how they sound. Whistlers, descending tones from lightning-generated pulses dispersed by the magnetosphere. Tweaks, sharp clicks with a ringing quality, from lightning-generated waves that propagate in the Earth ionosphere waveguide. Chorus, a dawn chorus of rising tones generated by energetic electrons in the radiation belts. And hiss, broadband emission from electron precipitation in the inner magnetosphere. These are all real. They are documented. They can be detected with simple equipment. A long wire antenna connected to an audio amplifier will pick them up on Earth. Amateur scientists and enthusiasts have been recording natural radio for decades. Some of them are genuinely striking. Chorus sounds like a chorus. Whistlers sound like someone blowing across the mouth of a bottle with slowly descending pitch. Tweaks sound like the plucked strings of a very deep piano. The moon has no radiation belts. It has no global magnetosphere to generate the plasma structures that produce most of Earth's natural radio. But it has its own versions of these phenomena, scaled to its own environment. The interaction of the solar wind with lunar magnetic anomalies can produce waves that, in the right frequency range and detected by the right kind of instrument, sound, when converted to audio, like organized tonal signals. The specific variety associated with lunar mini-magnetospheres is not yet named in the way Earth's natural radio is named. The research is too young, the measurements are too sparse, but the physics predicts that there should be analogous phenomena, waves generated at the boundaries of mini-magnetospheres, propagating along local field lines, dispersed by the local plasma, arriving at a spacecraft as structured tonal signals. When the Apollo 10 crew described what they heard as outer space-type music, they were, without knowing it, encountering a category of natural radio that had not yet been recognized as existing in the lunar environment. They were the first listeners of a phenomenon that is now being characterized scientifically, 55 years after the listening. This happens in science. The observation precedes the understanding. The description comes before the theory. The human ear, even when it's calling something music, is a sensor. And sometimes the sensor picks up something real before the theoretical framework exists to explain it. One final question is worth addressing, because it always comes up in discussions of this kind. Why does it matter? Not in the practical sense. The radiation shielding implications for future habitats, the deep interior mapping potential, the geological history encoded in the magnetic anomaly pattern. Those applications have been discussed. They are real and they matter. But why does it matter that the moon makes a sound? Why does it matter that a signal exists in the far side electromagnetic environment, periodic and structured, at a frequency no human ear can hear? The answer is both small and enormous. It is small because the signal is, in absolute terms, a minor phenomenon. It is not powerful. It is not influential. It does not affect anything that happens on Earth. The moon's electromagnetic whisper changes nothing about your life, your morning, your world. But it matters because it is another piece of evidence for the principle that keeps being confirmed across every discipline of science, every investigation of every part of the universe we have been able to reach. The universe is not empty. Not at any scale, not in any register. Everywhere we look with sufficiently sensitive instruments, we find process, we find structure, we find signal. The interiors of atoms are not empty. They are buzzing with virtual particles, with the constant exchange of force carriers, with the zero-point energy of quantum fields that cannot be quieted even at absolute zero. The space between galaxies is not empty. It is threaded with cosmic filaments of dark matter and hot gas, with the stretched photons of the cosmic microwave background, with the occasional stray proton travelling at nearly the speed of light from a source we have not identified. The surface of the moon is not silent. It clicks and ticks with thermal moonquakes. It oscillates with plasma wave activity. It carries a 22-second periodic signal that two different spacecraft have picked up decades apart, in the frequency range that instruments can measure. Emptiness is an approximation. Silence is an approximation. They are useful approximations in many contexts, but they break down when the instrument is precise enough, and the background is clean enough, and the question is specific enough. The far side of the moon is the cleanest measurement environment in the inner solar system. It was designed, by the accident of its geometry, to be shielded from everything human. And in that cleanness, the natural signal of the moon itself becomes visible. That is why it matters. Because it adds one more confirmation to the pattern. The universe makes sounds. It makes them at scales and frequencies and intensities that are outside the narrow band of human perception, outside the conditions in which evolution shaped our senses. But they are there, and every time we build a new instrument and go somewhere new and turn it on, we hear something we did not expect. The ancient Greeks believed the planets produced music as they moved, a harmony of the spheres, inaudible to human ears, perfected by their orbits. The idea was poetic and wrong in its details, but it was right in its intuition. The cosmos is not silent. It makes things, and those things propagate, and the propagations have structure, and the structure is, in the deepest sense of the word, a kind of music. Eugene Cernan called it music. He did not know the physics. He did not need to. He had the right instrument, the simplest instrument, and he used the right word. The understanding has taken 55 years to begin to catch up. It is catching up now. The investigation is open, the instruments are improving, and the signal, patient and indifferent and 4.5 billion years old, is waiting.